No.
You are. Here.
Nobody's okay.
Everybody is okay. Everybody just needs to relax. Everybody is okay. No exceptions. No, me too. Look, write this down. It is simple. Look, it's even titled simple. Yes, I know life is difficult. Yes, everything is difficult. Yes. English is difficult, math is difficult, physics is difficult, chemistry is difficult, coffee is difficult. Physics is the most. Life is difficult.
Math, physics, chemistry.
Be careful, this is recording now. Alright, simple harmonic motion. Relax. Right. Spring. That's a spring. This type of motion now, it's a special type of motion in physics. This type of motion that goes up and down, or left and right. That's what simple harmonic motion is. It's this type of motion. This is simple harmonic motion. So the spring is an example. What are other examples? Do you have other examples of this type of motion? You have a spring.
Rubber.
What else?
Plastic.
Well, no, like a clock. You know, a clock.
Pendulum.
Like this. This is also simple harmonic motion.
Because they're swimming, I think.
Huh?
So that's not they're swimming.
Oh yeah, but I mean, give me examples of motion that goes back and forth, left and right.
Oh.
Bell.
Huh?
Bell.
Bell, yeah.
Ding dong.
Clock, yeah. Spring. What else? Wave.
Yeah.
Ocean wave. You know, water goes up, then it goes down, then it goes up, then it goes down.
Yeah.
All of this is called simple harmonic motion.
Ocean.
Yep. So just like with circular motion, there's a special force that causes this. So you need this definition for the exam. If something is moving with simple harmonic motion, then the force is proportional to the displacement and acts opposite. Now, before you write that down, let me draw that for you. So what I'm saying is, if you have something like a spring, yeah. Yes, indeed. Here's the spring going up and down. What's happening here is there's a force this way. And what I'm saying is, the bigger the displacement, the bigger the force. So when the spring is up here,
There's no force.
this force, it's bigger than this force because the distance is bigger. Displacement. So look, here, no force.
It's stable.
No, just listen. Here, no force. Here, if I move it a distance, then there's some force. Here, if I move it twice that distance, then there's twice the force. And then if I move it 3 times this distance, there's 3 times the force. That's what I mean. And also, notice, if I move it up, which way is the force? The force is down. Which makes sense, think about it. If I pull the spring and let go, it wants to move this way. So that's what I mean in my definition. Proportional means the bigger the distance, the bigger the force. And opposite means opposite. The force is going the other way. You got that? Yes? Want to go on? Yeah? Not yet?
We didn't hit by and they're going exactly.
Moving. Okay. Yes? Okay, so I already drew, oh yeah. So I want to have a look at the time velocity graph. You don't need to write this, I need you to draw in a moment. So think about the spring. If I pull the spring up, look, and I let go, at the beginning, what's its velocity? No, just listen to what I'm asking, please. At the beginning, what's its velocity? Zero. Okay, and then I let go and it starts to move. Yeah. And it gets faster and faster, so it was lowest. Okay, so as it falls, it gets faster and faster. And then what starts to happen? Slows, stops, and then moves back up. Yeah, so I have the spring, I let go. Faster, 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 slow, stop. Up, like this.
Okay, but can your bullets out more?
Yes.
The velocity will increase?
Yes. Yes. Yeah. So, if you were to look at the graph, this is the time velocity graph. The velocity at the beginning is negative because which way is the spring going? Goes down. And then it gets faster and faster, and then it goes positive because then it starts to go up. Yeah, so this is why the velocity graph is going up and down, positive and negative, because the spring is going up and down. Okay? So you can just draw this graph as an example graph, because sometimes in the exam they ask you, draw a typical graph for simple harmonic motion. So what they want is to see this up-down movement. Huh? We could. But I'm talking about the final exam as well. Whoops. So just a picture is all I want. Did you draw it? It should only take you a few seconds to draw. Yeah? Okay. So there's some terms for simple harmonic motion. So we have, there are some terms which are common to the last lesson. Remember Ft omega. Okay? So the F, what was F? Frequency. So for example, if F is 2, it means the spring, for example, goes up, up, down in 1 second. Yeah. If F was 3, it means the spring goes up, down, in 1 second. What's the T? Yanni, I'll kick you out if you're going to annoy me. So just focus now. What's the T?
How many?
No?
Time.
The time. So it's the time for one movement. And finally the omega. What's the omega? Well, in the last lesson, what did omega mean? Yeah, what does it mean? Angular velocity, which means what? Yeah, but break it down for me.
Because it's like go up with angle. The spring when
In a circle, what does the omega mean in the circle?
How many radians per second?
Yeah, how many radians per second? So do you remember I said if the omega was 1, it means 1 radian per second? How big is a radian? 57 degrees, isn't it? About this. So that would be about this fast. Let me see, that's about, yeah, okay, so it'd be like this fast. Would be 1 radian per second. Remember that? Yeah. But what about for the spring? What could the omega mean for the spring? Because the spring is going like this, yes? There's no angles. So what could it mean for the spring? There's no angles. So what does it mean? Maybe, not this. It's still radians per second though.
It's still, the gap between straight.
No, not this.
But there's a circle because up and down like circle.
You see, I think you almost have it. You almost have it. It's like a circle, yeah. Let me show you. So I have a picture here to help you. So it's the train. So if you look here at the front, the piston is going back and forth, back and forth, back and forth.
Yeah.
That's simple harmonic motion. And then what's happening with the wheel? The wheel is turning. That's circular motion. So what I'm saying is, I think you kind of have the idea, when you have simple harmonic motion, you can always imagine, like in the picture, there's some wheel that's turning.
But it's like this.
What is? Looks like this. No, the piston here. This here is going left, right, left, right, left, right.
Yeah.
And this wheel is turning. So what I'm saying is the omega here is the same as the omega here. Or as you put it, Karar, when it's going up and down, it's like there's a wheel turning. Now I have an animation to show you which will be helpful. Huh? Let's see. Simple harmonic motion animation. This guy here. No, it's a little animation here. Yeah, look at this. So this is really a good example. This is simple harmonic motion. Can you see that? It's going up and down. And if you match that up with a circle, the omega represents how quickly the angle is changing here. So if the omega is very big, it's moving very fast. Can you see that?
Half of the wave is already.
What? You see this here is a spring. Can you see that? And this is going up and down, yes? So I'm saying if you match this with a circle, the circle is going round and around.
Yeah.
The omega represents how quickly this circle is turning. If you can imagine the circle with the spring.
Yeah.
That's what I'm saying the omega represents. So if this is turning really fast, what is this doing? It is moving really fast. Yeah, so if I go back here, big omega means it's going very fast, is my point. Okay, right. And I showed you the animation. There's the link for it. So if you have some terms, let me just go back to this animation for a second. You see this position right here in the middle? Right here, see this here? That's called the equilibrium or the origin. That is like the middle. It is the middle. It is the middle. The middle of the maximum and minimum. Yeah. So that's called the origin or equilibrium. It's the center, basically. The amplitude is the biggest. Yeah, the maximum is the amplitude. So if I pull it up here, this is the amplitude. It's the maximum. Velocity, velocity. Angular frequency, I just showed you in the animation. Frequency, frequency. Periodic time, periodic time. And you can see it's very similar to circular. I think the new words you should write down, which are the first two. So please write the first two down. Just the first two. Got it? Just the first two now. Yeah? Okay. Now we want to talk about the energy again. So if we imagine the example with the spring, if I pull the spring up here and hold it, does this have any kinetic energy? No, because it's not moving. So what energy does it have? Potential. And then when I let go, it gets kinetic energy. So what happens to its potential? Does it go up or go down? Goes down.
No, because the height will be less.
Yes. Now actually, the height, not the right word here, the length. Because for this example, you don't care about where it is off the ground.
So the length.
The length, yes, how long the spring is.
Yeah.
So it could be like this.
Yeah.
So if you pull the spring a lot, it has a lot of potential energy. And then when you let go, it gets kinetic energy, which came from the potential at the start. So if you were to look at the graph, so this is me just explaining that again. Oh, that graph is tiny. Oh no, that won't do. I'll have to draw it for you. So here is X and here is energy. So at the beginning, when the X is biggest, sorry, not X, we'll call it S, displacement in meters, in joules. Okay. At the beginning, A, does it have any kinetic energy? No. And then what happens? Look please, when the spring gets smaller, what happens to the kinetic energy? Becomes bigger, because it goes faster. When you let go, it goes faster. So as the X gets smaller, you get more kinetic energy. And then what happens? When it reaches the bottom, it starts to slow down.
Potential getting.
And yeah, then the other way. So it slows down, and then back here at minus A, no more kinetic energy when it goes all the way down. Now what about the potential energy at the beginning? It's very big, isn't it?
Very big, yes.
But then as time goes on, what happens? It decreases. So it's actually exactly the opposite. So in blue is potential energy. When you add the two energies together, you get this. In green is kinetic energy plus potential energy. And notice how it's constant. But it should be constant because the total energy doesn't change. Did you draw that? Yeah?
And the first kinetic energy is less than here, right? Kinetic.
Where? Beginning?
Yeah.
The kinetic energy is in red.
Yeah, but it's less than at the end, right? The kinetic energy at the first. It's less than the kinetic energy on the end.
At the minus end?
No.
Like on the graph here?
Yes. So here's the kinetic energy.
Yeah?
This one.
Yeah?
Okay? The kinetic energy here is less than here or more?
Where? Here?
Yes, here.
Well, this is the kinetic energy is increasing.
Increasing.
And then here is the kinetic energy is at maximum.
Maximum.
And then it decreases. Back to zero.
Okay.
And then at the beginning the potential energy is maximum.
Maximum.
Then it decreases. And then it increases again. Yeah? Okay. Can I go back to the slides?
Yes.
Yeah. So that's my tiny picture. Oh, that's also tiny. But I don't need you to draw that, I just need you to picture it for the moment. So if you have your spring like this and you let go, what happens to its velocity? It goes faster, 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 slower, 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 slower. So if you were to draw the graph we saw earlier, it goes up, down, up, down, up, down. Now what about the position? Well, here's the position, the x. Here it's big, and then it's small, 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 bigger, 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 bigger.
Yeah.
And then what about the acceleration? The acceleration is also the same. It goes big and small, big and small. So these three graphs are just to show you that you get the same picture for distance, velocity and acceleration.
Distance, time, velocity, time.
Now wait, just think for a moment. Acceleration is like force, isn't it? F equals ma. So when is the force biggest? Up here or down here?
The next question is B.
Yeah, we're just telling you A or B. When is the force biggest? A.
Yes.
Because the distance is biggest.
So the acceleration is below the velocity here.
So here the acceleration is biggest.
And the velocity is bigger.
No, smallest, because it starts at
Opposite.
opposite, yes, exactly. So the acceleration will be opposite the velocity. When the velocity is big, the acceleration is small. So can you make note of that? When the velocity is big, the acceleration is small. And when the velocity is small, the acceleration is big. So they have this opposite relationship.
The opposite.
Yeah. When one is big, the other is small. Yeah? Oh no, I don't like this. I don't, please use English, please.
Yeah.
So, you can look, you don't even have to use much English. Watch. Watch. When V big, A small. When V small, A big. Now what's wrong with this? Yeah, there we go.
It's English.
That is English, yeah. There's nothing wrong with English. Okay, going on. So, we have some formulas here. So the first one, please write this down, it's the same. T equals 1 over F. Yep. Second one, also the same. T equals 2 pi over omega. Now I think we start to get different. Number 3, the acceleration is now minus omega squared x. What was it for a circle? Do you remember? B squared over r. Now it is minus omega squared x.
What's the D? What?
X, sorry I should say x maybe. X is the displacement. Yeah, I should change that to S actually. Let me make note of that. X needs to become S, and my pictures are too small. Okay.
So
Yeah.
Omega square S.
Yeah. If you like. Now, it depends. A lot of books use K or S. It doesn't matter. Now, here S equals A sine omega t, but please,
A, acceleration?
no, amplitude.
No.
Amplitude A. Now I need to explain my note beside this.
Yeah.
That's time?
T, small t time.
We should be using battery?
No, because it's not periodic time. It's any time. Yeah, no, I'll explain the note in a moment. No, you can wait in a moment. Okay. Firstly, that small t is not a mistake. That small t is not the same as the big T. What does the big T mean? Periodic time, the time for one movement. The small t can be any time you want. So for example, you can do like 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, 6 seconds. It's any time you want. Okay, whatever time you want. So that t is the time.
But
And just like that big A is not acceleration, that big A is amplitude, the maximum displacement. Yeah.
so both big T and periodic.
Big T is periodic time. Yeah.
Nothing common to
Correct.
Otherwise?
Yeah, no.
Okay.
I'm going to explain it. Yeah, the big A is maximum displacement, yeah. Okay, now please note, I said, look at me. It's not too bad, I know, look at me. So, I said to use sine here. You use sine when it's like this. You pull the spring, and it's at its maximum at the beginning. That's when you use sine. But sometimes you could have it like this, where, imagine you have the spring, and you knock it and start it moving.
Knock it.
Yeah, like you flick it.
Oh, you press it down.
No, that would be sine. So for example, watch. Imagine there's a spring here, okay? So if I press it down, hold it, and let go, I use sine. But if I have my spring, and I just knock it, I don't move it, I just kind of give it some force to make it start moving, then I use cos. Now those might seem similar, but they're different. The first one, I do it slowly. I go push it down, I hold it, I let go and it starts to move. I use sine. But if I give it some speed, then I use cos instead.
You also press it.
No, not press it. No, not press it. I give it some speed. I start it moving. I give it a velocity. The difference is this.
The velocity.
Yes.
So it's down or
No. Watch. I push it down slowly and I hold it. Does it have any velocity? No. Let go and it starts to get velocity slowly. The other option is the spring is here. I don't press it, I knock it. So I give it velocity from the beginning, a big velocity at the beginning.
Oh, then it won't be going that will be moving.
We're making this difficult, yes?
It's just up and down almost.
No, it can be up or down or left or right, yeah. It's the same. All the formulas are the same. Okay, look. Think about it like this. You know you have the pendulum.
Yeah.
Okay? So the first choice is you pull it up to the side and you let go and it starts to swing. That's sine. The second one is the pendulum is here and you come along and you go, you hit it and you start moving. That's cos. You might need to sleep on this and think about it, okay? But please note, usually it's sine. Usually it's sine, but sometimes it could be cos.
You can skip now.
Right, the next formula is... Yes? Which one? Omega. Yeah.
No. These have speed.
Has D? This? Speed? What do you mean? Like what? Yeah? Ah, yeah. So, this one here, you don't give it speed. This one here, you do give it speed. Now you should say, wait, no speed at start. And then here is speed at start. Okay. Now the next formula is for the velocity. A omega cos omega t. Now wait. Before you start, hang on. Oh wait, sorry, I made a mistake here in my slide. My sines and cosines are backwards, so sorry. It's terrible, life is difficult, I know. So sorry, but good thing I realised it now. That sine should be a cos. That cos should be a sine. That cos should be a sine, and that sine should be a cos. They're all backwards. Everything is backwards.
Okay.
No, it's still the same. Sorry, so
They're still the same.
this is a cos and this is the sine. This is the cos. This is the sine. Swap all the words. I know. I'm so sorry. I'm sorry. It's terrible. I know. Everything is terrible and difficult, I know.
Everything is to understand now.
Now you can understand it?
No.
I'll fix it here. I know. Life is difficult.
So we usually use cos sine.
So we usually use cos, yes. Not sine. Look, let me change. Sine is cos. Cos is sine, cos is sine, sine is cos. You don't understand, I have to type all of this. It's difficult. Look at it.
You can make it more easy. Just start in the word.
No, because this looks beautiful this way.
This it doesn't have to. You want to. So
You want it to look beautiful too. Admit it.
that's not you actually.
What?
That's your work.
What, my work? Yeah, you want
Make it though.
You want it to look nice, don't you?
Just use the idea of PDF to type this one way.
PowerPoint. Ugh. PowerPoint is ugly. I don't like ugly. Well, try it. Small graph, formula A. And then the next one is B.
A omega sine omega
Yeah.
t.
Yes.
So when you press through it, then you use
Cos.
cos.
Yeah.
No,
That's what I've been saying. I got it backwards. It's fixed up here now. Now I tell you how I know it's a mistake. If you think about this, can you look please? Again. So if you do this, if you hey look, come here, look. If you push it down like this, at the beginning what's the velocity? Zero. Now look at the formula. What is A omega sine omega 0? What's sine 0? Zero. Which is what you want. You want B to be 0 when the time is 0. So if you do it like this, you push it down, you have to use sine again. And likewise, if it's you knock it, then you use the one with the cross for the velocity. This is how I know it's my mistake, because I know at the beginning when the t is 0, the v is 0, so that means this one here should be sine, because sine 0 is 0.
Cos 0 is 1.
And cos 0 is 1.
Oh, okay.
So this is how you can also remember which way around it is, because you want sine the v to be 0 at the start if it's like this. Okay. No? Yeah, I know, me too. This one here, yes, this one here, yes.
You should be able to string for this.
Yeah? What's your question? No, this is right.
No.
Yeah?
Yes.
Yes, you go like this and then you let go.
And this is not.
This one is, yeah, you flick it, yeah.
Just freezing.
Yeah, so you go like this and it starts to move. Yeah?
If you see that,
So yeah, this one here is you slowly push it and then you let go. This one here is you knock it and then it starts to move. Push slowly. Yeah. And then this one here, hit fast.
you should give it a
Knock fast, yeah.
What is not fast?
Hit it, no, just hit it, like knock fast would be like that. Like a quick hit and it starts to move. Yeah, the same. This one goes with this one and this one goes with this one. So yeah, this one here is also the same.
And this is push slowly.
Yeah, the same as this one, yeah. And this is not fast, yeah. Oh, good. Okay. And now this is the formula for acceleration.
Almost for acceleration.
The plus and minus depends on which way it's moving. If the force is up, it's plus, and down is minus, yeah.
Up is plus, down.
Yeah. Left is minus, right is plus.
X squared. Change it to S squared?
Yeah.
Square.
Okay.
I should tell you F is displacement. This should be F as well if you want.
And this is
Velocity. Speed, yeah. Okay. And then the last formula is the formula for potential energy
Of spring.
of the spring. And again, you can change that to X if you like. A half M omega. Most books would be X. Half M omega squared F.
The spring is sideways.
It doesn't matter. It's still the same. Yeah, so this is potential energy of the spring, not because of gravity. Now, think about it. This makes sense. If the X is really big, then what's the potential energy? Big or small? Big. Which, makes sense. If you do this in the spring, there's lots of energy in it. And then when you let go, it gets converted into a lot of kinetic energy. So it makes sense that the bigger the X, the bigger the energy. I should also point out, the last formula is not in the formula book, but it is in the exam. So you should make a note that this formula, you need to remember it because it's not in the book.
You will give us in the physics exam, you will get the formulas.
But not
All of it.
all of them. So in the book, you'll have 1, 2, 3, 4, 5. For some reason, 6 is not in the book.
The exam will give the formula?
Oh my goodness, that's what he just asked me. Yes, I will.
On this time.
Didn't say that to us.
I know, it's a surprise for you.
Something they're giving it that. They do.
I know, because I've done this for 7 years, and each year I give the students the book. So I know this.
And then final?
Yes.
Never exam.
Yes.
In a midterm exam.
Except that one. Because I want to see if you can remember them. Alright.
You exempt?
Now, in the real world, the motion is not like this. So if you pull a spring down, It goes up, down. But does it continue to do this forever? No. It actually goes more like this. Yeah. So we call that damping. It decreases. Now we don't do this in physics because it's too difficult. We imagine that it continues like this. But of course that's not what happens in the real world. It damps. This is called damping. So I just want you to learn this word, damping. The only question that could be about this in the exam is explain what it means.
And that's fine.
And that's fine. Damping means when it goes like this.
How to write it?
Yeah. Draw a picture, how do you write it in words? You could say that damping, a picture plus damping is the slowing down of the spring over time. If you want those words, I'll help you with your words. Damping is the slowing down of the force over time until the force equals 0 and stays at 0. Slowing down of F over time. Damping is the slowing down of F over time until F equals 0, and then it stays at 0 forever. Yeah, obviously, yeah. Yes? What? No, I still need to do an example and then we'll finish. Yeah, just relax, okay?
No.
My stomach is talking to me.
Yeah, I know, and my students are talking to me. So when my students stop talking, I can finish sooner, and then you can go and listen to your stomach. I know. Look, just hang on. Hold on there. The last one I couldn't find a good picture of. I'll talk more about this next time. So don't close the pen. I need you to do examples. A boy again. So look, I'll do, I have...
One guy. Pick one.
Pick one.
This one.
No.
Yeah, this one.
This one.
This one.
Molecule.
Yeah. So look, in this one here, what's happening? You've done molecules with Lorraine.
Yeah, I hate that. No, not Lorraine, molecule.
So this molecule is vibrating. The molecule is shaking. Yes? All molecules do this. So what I tell you here in this question is that the frequency is this, 8.25 times 10 to the 14. So is this moving fast or slow? Very fast. Very, very fast. And the amplitude is 74 picometers. Anybody remember pico? 10 power
12? 15?
minus firstly. Correct.
Yeah.
Yeah, what he said. So that's the amplitude. So my first question is what is the omega? Question 1 is what is the omega? Okay, what's the formula for omega? 2 pi over t. Oh, but you don't know what t is, do you?
No. Time is 1 over 2%.
So you can get t is 1 over f. So yeah, t is 1 over 8.25 times 10 to the 14. So you can put that back in here and get omega is 2 pi over t, which is 1 over that number. So omega is 8.25 times 10 to the 14 times 2 pi. Can you just multiply this piece with this piece? See what we get. 8.25 multiplied 2 pi. What's that, please? KJ, what is it?
61.8
times 10 to the 14 radians per second. So it's moving really, really fast. Next question is, you got that? What is S when t equals 1 microsecond? So I want to know what the S is after 1 microsecond. So what formula could I use here? S equals, oh no,
A
cos
WT.
omega t. What is S?
P. No,
P?
No.
Micro. Here, this one, yeah? 10 minus 6. Micro. You remember this word, Grace? No, micro. Okay, so S is A. Where's my A? 74 times 10 to the minus 12. Cos omega 51.8 times 10 to the 14. T. And the T is 1 micro. KJ, can you type this in, and for goodness sake make sure the calculator is in radian mode.
1 times 10 to the power
74 times 10 minus 12, cos 51.8, 10 to the 14, times 1, times 10 to the minus 6. What do you get?
Very easy to make mistake here.
When you put in the rating mode,
Please remember to put your calculator in radian mode.
What kind of?
It's usually something like shift and mode. Sorry, I'm finished here in a sec. Are they waiting outside? They give this, or will I tell the students this, or will they get a copy of this?
No, I'm gonna.
Oh yeah, sure, it's fine, yeah. They have the same on Tuesday, and then the maths is on Tuesday. Yeah, that's fine.
Yes.
Yeah, they don't need this, no?
I'm gonna.
You're gonna do it.
Yeah.
Okay, alright. And that's the number there.
you want an email?
I don't know.
What's it?
No, don't worry about this. Okay, look, I haven't got time to finish this. What I'll do is, I'll do the examples in the office and upload them, okay, so that you can see them. It's a little bit rushed at the end here. I'll do the examples in the office and upload them. Yes? Get out of here.
Yeah, okay.